Right, and the next talk is about learning pseudo backdoors for MIPS, and Aaron Ferber will give the talk.
Can you hear me? Hello? Oh, okay, cool. Great. So yeah, hi, I'm Aaron Ferber. I'm a PhD student at USC working with Bistra Dilkina. And today I'll present work on learning pseudo backdoors for mixed integer programs. And this work with my collaborators, Jialin Song at NVIDIA Labs and Yisong at Caltech, and my advisor, Bistra Dilkina. And so that was a great presentation about MIP. And just to be sure we're on the same page here, yeah, I'm trying to solve MIPS fast. Overall, like they're a very flexible modeling framework that can solve a wide number of combinatorial optimization problems in practice. And we're just trying to find a setting of the decision variables X that satisfy these linear constraints and some integrality constraints with a linear objective function. And so the standard approach to MIP, as we just heard Alon talk about, is the branch and bound algorithm, which has a lot of, this expertly designed heuristics and things that we want to take advantage of. And a lot of those heuristics involve things like adding cuts, running primal heuristics, randomly restarting, calling like vague function calls and subroutines. And what we'll focus on is how we can select valid decision variables for branching on at the top of the branch and bound tree. So our goal here will be to try to predict which variables we should prioritize for branching before we start branching. And we're going to tackle this problem hopefully with machine learning. And in that sense, our goal is to train on a data set of instances and then deploy our model on a new collection of instances that we haven't seen before. Right. And so for our approach, we took a look at this idea of a strong backdoor. And so in the combinatorial optimization literature, a strong backdoor is a subset of the decision variables such that they're core to kind of quickly solving the optimization problem. So if we restrict, for instance, the branching in branch and bound to this core set of decision variables, hopefully we can find an optimal solution. So in this case, B, we consider this like B to be a backdoor if when branching on only the decision variables in this backdoor set, we reach the optimal solution that we mark by the star in this kind of figure of branch and bound tree. And so the benefit here obviously is that if you have a small backdoor set, right, and you solve your MIP with this strong backdoor, then you can really limit the size of your branch and bound tree. The problem is that obviously if I could give you small strong backdoors, you could solve MIPS really fast and you would have nice runtimes. So that's a little bit intractable. The other downside is that if your strong backdoor is incorrect, if you make a wrong guess, as machine learning models are very well known to do, you will end up with a solver that doesn't actually even find your optimal solution. It might not find your feasible solution, right? If you restrict branching too much to a subset of incorrect decision variables, your optimal solution may lie outside of that branch, right? And so for that reason, we consider the idea of this pseudo backdoor, which the idea here is that we're considering still a set of decision variables, and we're going to say, try to branch on those decision variables if you can. And then if you run out of decision variables in your pseudo backdoor, you can just default to any other of the fractional decision variables at the current node in your branch and bound tree. So you can kind of see in this graphical sketch that you still have kind of the same backdoor as before, but if you make a mistake with your machine learning model, you can default to branching on other decision variables. And the other benefit here is that I can evaluate these pseudo backdoors along different empirical metrics that we're interested in. And so we can try to identify these pseudo backdoors that either yield faster solve time, close the gap quickly, or yield high quality solutions at a time cutoff. In particular, for our case, what we're interested in is just faster runtime, but our method is flexible enough to capture these other properties of interest. And so previous work in machine learning for optimization, there are a number of previous works at this point. Many of them are here. But I'm specifically just mentioning these, but there are many others. And so initially, there's a lot of machine learning for optimization literature in the space of predicting branching variables in the branch and bound tree. And those are really kind of tied to what variables should you select at the current node of the branch and bound tree, kind of rather than at the top of the branch and bound tree that we're trying to do here. And there's an interesting survey published that has a lot of work in that space. The other kind of vein that I'll point out that's very related is trying to do machine learning at the top of the tree search. So trying to configure the algorithm hyperparameters so that you can just run your solver with while feeding in the hyperparameters without kind of tinkering with the individual variable selection. And so our approach kind of lies somewhere in the middle. We're trying to determine this thing, the pseudo backdoor, which is inherently related to the structure of your problem, but we're trying to do it at the top of the branch and bound tree. And so then backdoors, as kind of a little bit of a long history, is that it was initially introduced for SAT and CSP. And then later in SAT and CSP, there is some limitation in the fact that people have discovered they're not empirically practical. But in MIP, people have found that strong backdoors exist. And there are efficient ways of sampling them. Initially, people proposed you can potentially sample them using the LP relaxation. So sampling variables into your backdoor based off of the LP fractionality. Just note that it's not like LP fractionality branching that I guess most of us know doesn't work. It's generating a backdoor based off the LP fractionality. And other work kind of tries to cover the set of decision variables using backdoors. And very recent work shows that you can create an efficient sampler using Monte Carlo tree search. That's this interesting work by Khalil and others, where you use Monte Carlo tree search to try to limit the size of the tree weight, and that operates on the fly of the solver instead of kind of training offline. So in our approach of learning pseudo backdoors, our ultimate goal is to train a model on a data set of some expensively collected examples, and then deploy it on an unseen instance in order to quickly solve that unseen instance. And so you can imagine in practice, you might be solving your knapsack problem every day or so. And so you want a fast solver for your distribution of problems. And so that's the setting that we're in. Our approach itself consists of this kind of two-part model. The first part is a score that tries to, that takes in randomly sampled pseudo backdoors using previous work that has good sampling methods. And what it does is it scores each of these pseudo backdoors according to what it thinks is the quality of the pseudo backdoor in terms of how fast it will solve the MIP. Then the score ultimately predicts, okay, which is the best sampled pseudo backdoor that you gave me. And then after the fact, since it's potentially the case that there are no good pseudo backdoors for your given problem, and you really want the greater flexibility of branch and bound or another state of the art solver, we have a classifier that classifies whether the predicted pseudo backdoor will be a state of the art solver, either Gurobi or skip or express a very state of the art solver. And so just graphically, here's our pipeline. We take the MIP here, we solve the LP relaxation to generate samples of our pseudo backdoors using the previous work by Dilkina and others. These pseudo backdoors are encoded as a graph, and they're scored with our kind of deep learning model that I'll get into later. This ultimately gives us like a predicted pseudo backdoor, which is then classified, and then we run a solver either with just plain Gurobi or by increasing the branching priority on the variables in the pseudo backdoor set. Right. And so the way the scorer works is it takes in a given pseudo backdoor, and then it encodes it using this bipartite graph representation that was in previous work. And essentially the bipartite graph representation, what it does is you have two sets of nodes. You have nodes that represent decision variables and nodes that represent constraints. And with this graph formulation of the MIP, is essentially a relatively flexible way of describing the MIP. What we can do is we can feed it into a wide variety of deep learning models that kind of take a graph and run some classification or scoring on the graph, right? So you can imagine in the machine learning literature, there's a wide variety of approaches here, and we leverage one of those approaches. Ultimately, we feed it through our kind of graph convolutional network, graph neural network, and we're left with just a single score. And then what we do is that we run the scoring module on all our scoring MIPs and select a candidate backdoor. And then downstream, we actually have the same pipeline for the classifier because we need to determine whether or not the given candidate backdoor will beat Gurobi. Right. And so to go into a little more detail on the, about the encoding itself. On the left here, we have variable nodes, and on the right here, we have constraint nodes. And we also generate an edge between a variable and a constraint if that variable appears in the constraint. So it kind of related constraints to the variables. And in addition, on every variable node, we have a bunch of variable features. On every constraint node, we have a bunch of constraint features like how close is it to the objective function and what's the status in the root node. Notably, compared to previous work, the main difference is that here we're doing this at the root node of the branch and bound tree. So we don't have any access to anything like pseudo cost. I guess unless we're doing restarts, I'm not sure about that, but we don't have access to kind of the internals of the solver at this point. And to get a little more into detail in terms of the graph neural network itself, these equations are kind of overly complicated, but overall what it's doing is the graph neural network, it will encode each of these nodes at the next layer based off of the related nodes. So let's say you're a variable node, your next layer's embedding should be a function of the adjacent constraints that you're a part of, right? And if you're a constraint node, your next layer's embedding should be a function of the variables that kind of appear in you as a constraint, right? In addition, we say that a variable node should be kind of, the next layer embedding should also take into account itself. The other thing that we looked into was using attention. And so this longest equation here for some reason is just an attention module that says how much should it care about any, like the messages coming from the different constraints. And those messages are kind of computed using another neural network, right? But the main idea here is that this is a very expressive model that can capture a lot of intricacies in the pipeline. And so then ultimately, after we get all these high-level embeddings, we aggregate them and pull them together into that single value that we need, either whether the pseudo backdoor will be Gurobi or not, or how good it is relative to the other pseudo backdoors. Okay, so in order to train our model, we need to collect data. And luckily in this setting, the data is relatively easy to collect. And so what we do is we're given a bunch of training MIPs. And for each of those MIPs, each of our potential like knapsack instances, we're going to randomly sample our pseudo backdoors according to the LP fractionality. And we're just going to score each of them. We're going to ask, okay, solve using higher branching priority on each of those training MIPs, and tell me how fast did you solve. If we're looking at other metrics, we could say, what was the solution quality at the time cutoff, or what's your primal dual integral closure. But in this case, we're just looking at runtime. And so once we generate this data set, we also collect information about how fast Gurobi solves so that we can compare pseudo backdoor performance against Gurobi performance. So after we've generated this kind of complicated or this expensive data set, we train our score by training the machine learning model to effectively rank backdoors in the data set. And so what that looks like is essentially we feed each of these backdoors into our machine learning module, and we train the value estimator to output values such that better backdoors are ranked better than worse backdoors, right? And so the main idea here is that we don't want to directly predict runtime because there are a lot of other confounding things. Each individual MIP might have different runtimes. The thing that we care about is which is the best backdoor among the set of candidate backdoors. And then after that, classifying whether or not machine learning will beat Gurobi is a relatively easy task. It's just kind of a binary classification task. We just trained our second model to say, will the input backdoor beat Gurobi or not? And that's kind of a simple binary classification that we just minimize cross-entropy loss for. We perform experiments on 3 settings, this neural network verification setting, where you encode your neural network as a MIP and you try to see how robust it is to perturbations in the input. Facility location, where you want to know where to start up facilities to satisfy customer demand. And the generalized independent set problem, where the overall goal here is to find an independent set of nodes, but you can additionally pay a cost for deleting some edges which are currently preventing your set of nodes from being independent. And this problem was originally proposed for forestry management. So in each of these settings, we have 100 train, 100 validation, 100 test MIPS, and for each of them, we generate 100 pseudo backdoors for training on. So it's a relatively expensive to collect data set, but once we have it, we can just throw kind of deep learning at it and see what happens. And so overall, this is what happens. So in these diagrams, we evaluate Gurobi in blue against kind of the score itself in orange and the full pipeline in green. And here, the score itself is deployed by just running whatever was predicted to be the best pseudo backdoor. And then the score plus the classifier is that kind of full two model process that I had described earlier. And so the main thing here is that the score sometimes does well and it sometimes doesn't, right? So in neural network verification, facilities easy, and generalized independence at hard, it seems that score is doing kind of on average better than Gurobi, and we'll look at win-tie loss better. But then in some other instances, it's kind of really losing on GISP easy and facilities hard. And what we found is that essentially the score is having some major wins, but again, when it loses, it kind of really loses to Gurobi. It's really predicting backdoors that increase the runtime a lot. And we saw that in this win-tie loss table. So here, I'm just printing out kind of each of the domains, and Gurobi is kind of the top one. The score by itself is the middle one, and the score plus the classifier is the last one. And the key thing to look at here, kind of forget these numbers over here, is the win-tie loss rate of the score by itself and the score plus the classifier, the full pipeline. And so the main thing to note is that the score by itself seems to have a large number of wins on each of these domains over Gurobi, so 68, 65, 28, 41, and 47. But then the issue is that it does also have a large number of losses, and those large number of losses contribute to the decreased performance on average. But then the score plus the classifier overall is able to maintain a large number of the wins that our score had, while simultaneously reducing some of the kind of losses to Gurobi. Just as like a small note here, we record when it chooses Gurobi as a tie, but in practice we get a small runtime penalty because we had to run the classifier on top of everything. This is just for to understand actually what's going on under the hood, right? And so the key takeaway here is that the score by itself is able to give us some good wins, but the classifier is able to kind of minimize the losses relative to Gurobi or another state-of-the-art solver. Right, and so the takeaways here are on the optimization side, it seems promising to identify these pseudo backdoors for a given MIP, either on the side of solving or potentially on the side of gaining some insights into the problem. And then on the machine learning for optimization side, kind of the area that I'm working in is that making predictions at the top of the branch and bound tree can kind of help front load the computational cost of running experiments and simplify the machine learning modeling into something like ranking and classification, rather than difficult Monte Carlo tree search or something like that. And the other thing is that we can have overall improvement from identifying whether we should use our machine learning models or use standard Gurobi, and that our machine learning models in particular gained improvement by kind of taking as input the actual object that we were predicting, the pseudo backdoor itself, instead of just saying kind of, should I ensemble between these two? So thank you for your time, and please let me know if you have difficult distributions of MIPS to solve. I'm looking eagerly for them. Thank you. Yeah, Elias.
Yeah, so can you go back to the slide where you have the scoring and then just the overall architecture?
Oh, yeah.
So at test time, how many of these BIs, BKs do you sample?
So here it's still the same number, still around 100.
And then do you have a guarantee that the highest scored BK is, kind of the next network is monotonic in that? So if B2 gets the highest score, and then, it should, any other
Right.
B should always lose to it, at least when you compare it to Gurobi.
Yeah.
That's gonna happen.
That's, I'm almost positive that's not going to happen. But that's a really good point in, like, maybe I can design this or a second level architecture that ensures
I
that.
think there's a simple solution. You just learn to predict the running time, and you also learn to predict Gurobi's running time. And then you can just keep sampling until you get something that the model thinks is gonna get a smaller running time than Gurobi.
Right.
Then you don't have to know that you need 100, and you get monotonicity for free.
That's true. I guess we didn't try kind of the stopping criteria of keep sampling until you have something that's going to beat Gurobi. But we did try the kind of runtime regression, and we were unable to get good performance in runtime regression to ensure that. Maybe runtime regression plus ranking could work.
It can be relative to.
Or yeah, like either relative to Gurobi, like predict something normalized by Gurobi's running time. That could be possible. But we did see it like a very kind of heavy tail distribution in terms of the overall running time, which was hard to model against. But yeah, some other preprocessing could work. Yeah, thanks. Yeah, or oh, okay. Oh, yep.
So I kind of have a two-part question. The first one is there a way to quantify the extent to which a BI is a pseudo backdoor?
Right. So I guess with pseudo backdoors themselves, since we're evaluating them in terms of runtime, you would just say, oh, does it beat Gurobi or not?
So that's really my question, right? The theory here is you're finding this set, and it's a good set because it's a pseudo backdoor, right? But in the end, you're just looking at runtime.
Yeah.
And so there's no connection back that says it's because it's a pseudo backdoor that it's working.
Right.
Right. It might be some other reason that it's working.
Right. Yeah, it's kind of mainly a heuristic to guide where we're going in that regard. But I would say at the end of the day, we still can evaluate kind of whether or not it's a strong backdoor. Like we can evaluate at what frequency there's strong backdoors, but we found that for most of these problems, it was hard to find actually strong backdoors. So it is kind of in the original picture, it is kind of this scenario where your branching requires you to go outside of your
But if you want to improve your performance, you kind of want to understand if the reason the performance is good, you're headed for backdoor, right?
Yes, the plot from our paper actually has a metric, which is the 3-weight, which is the number of total 2 to the n solutions that you've eliminated by branching on the small set, even though it may not be a strong backdoor. So that plot actually has such a metric which correlates with likelihood of being a strong backdoor. Yeah, that's
that's true. Yeah, we should evaluate the tree weight metric. I think that would be good. Thanks.
Other questions?
So when you define a backdoor as part of like through Gurobi's prioritization, is this actually a soft or a hard prioritization? Do you know that?
I mean, I guess I don't know that for sure since I don't work at Gurobi. In their documentation, it says that they require branching before on high priority backdoors before other backdoors. But I guess I'm not sure of the internal.
Well, for example, skip has both, right?
Yeah.
Skip has a like soft, like just like adjustment of the actual scores that you like compute. Like and then just a variable that to which you give like a 10 multiplier, right? This will like be branched on more likely. And then there's also a hard cutoff where you only consider variables of priority first. And this is why I was asking, because actually your backdoor can be not that good, right? But you just save time in evaluating branching decisions, kind of. If Gurobi decides to do a more like, I don't know, strong branching or whatever, you might just reduce this. So it might also be interesting to look at the number of nodes, right? Whether your backdoors actually help the search or whether it's basically, we are basically cutting strong branching.
Right. And I think to even look at other metrics like tree weight, we'll need to pivot to something like skip, which might take longer, but.
I'm always for tree weight.
Okay, cool. Thank you.
All right, thank you.